So Hidetaka Houtani is our next speaker, and so he is an assistant professor in the Department of Systems Innovation at the Graduate School of Engineering at the University of Tokyo. So he received his PhD in environmental engineering from the University of Tokyo in 2015. Before his appointment as faculty at the University of Tokyo in 2019, he was researcher at the National Maritime Research Institute in Japan between 2012 and 2019. So his research interests include ocean waves, particular interest in freak waves, seakeeping of ships, and ship hydroelasticity. And with that, Houtani, please start your talk. I'm looking forward to seeing these new results. Houtani, the floor is yours. Thank you.
So thank you for the introduction. I am Hidetaka Houtani from the University of Tokyo. And thank you very much for this opportunity to give a presentation. And today I'd like to talk about our research entitled on the crest-height amplification of unstable Stokes wave trains in deep water. So rogue waves in the ocean are potentially devastating, potentially a dangerous phenomenon that can cause a devastating structural damage to ships or offshore platforms. And especially for fixed offshore platforms, the crest height of rogue waves is of great concern for designing. This is because the air gap is the height between the crest and the deck of the platform has to be large, sufficient to avoid a large wave load acting on the platform. And recent studies have revealed that the modulational instability due to nonlinear quasi-resonant interaction plays a vital role in generating rogue waves. And such a nonlinear wave evolution is governed by the balance between the nonlinearity and dispersion. And this balance is well expressed by key parameter, the ratio between the wave steepness and spectral bandwidth. And related parameters are introduced and investigated in several research studies. And for example, the Benjamin and Feir index or delta parameter. And modulational instability phenomena was first discovered by Benjamin and Feir, and they found that the Stokes wave is unstable to sideband modulation. So if a sideband perturbation is added to Stokes wave, and here the sideband wave number is slightly upper or slightly lower than the carrier Stokes wave number. In such a case, and this key parameter, the ratio between the nonlinearity and spectral bandwidth, is larger than this value, the sideband amplitude grow exponentially. So therefore, the wave deforms largely like this figure, and large wave appears in the wave group. And this is one of the fundamental mechanism of the rogue wave generation in the ocean. And it is known that the nonlinear Schrödinger equation well describes such nonlinear wave evolution due to modulational instability. And this describes the nonlinear temporal evolution of wave envelope A. And Akhmediev breather solution is one of the analytical solution to this NLSE. And this AB solution describes the temporal evolution of unstable Stokes wave trains. And this AB solution, from this AB solution, we can derive that the ratio between the maximum amplitude and the initial Stokes wave amplitude is described like this as a function of this key parameter. And in the limit of zero spectral bandwidth, this amplification factor can reach 3. However, several fully nonlinear numerical studies indicated that the maximum amplification can exceed 3. And the physical mechanism of such crest enhancement exceeding AB solution is yet to be clear. Therefore, the objective of this study is to clarify the physical mechanism of such crest enhancement through tank experiment and numerical simulation using higher order spectral method. And I will show that these 3 processes, spectral broadening, band wave production, and phase convergence are crucial for such a crest enhancement. So moving on to the facility and method. And in this study, we investigated the modulated wave train with these parameters. And the initial wave profile is given at the 3 wave systems like this: a carrier wave and upper sideband and lower sideband waves. And wave steepness was swept between 0.08 to 0.115, while the perturbation wave number, spectral bandwidth, was fixed to 1/7. And this parameter range includes both the non-breaking and breaking waves. And the temporal evolution of the unstable Stokes wave train is was simulated by using the higher order spectral method. And this HOSM numerically solved the Laplace equation of the velocity potential phi subject to these free surface boundary conditions. And these boundary conditions is described with the surface elevation zeta and the velocity potential defined on free surface pi s. And these free surface boundary conditions are expanded to arbitrary nonlinearity order perturbation series up to arbitrary nonlinearity order n. And in this study, m equal to pi, nonlinearity order is adopted. And the temporal evolution of zeta and pi s is solved numerically. And the spatial derivatives terms is solved in the wave number domain using FFT. So this means that spatially periodic boundary is assigned in the HOSM simulation. And HOSM can take into account the quasi-resonant interaction, and there is no restriction on the spectral bandwidth. And we also performed a tank experiment generating corresponding and stable Stokes wave trains. And here we use the HOSM wave generation method, and the outline of the HOSM wave generation is illustrated here. And first, we simulate the temporal evolution of modulated wave trains using the higher order, using HOSM. And using the HOSM output, the wave maker signals that is temporally evolving, like this figure, is calculated. And giving this signal to the wave maker, we can generate spatially periodic and temporally evolving modulated wave trains in the wave tank. And the experiment was conducted in the wave tank at the National Maritime Research Institute. And in this experiment, the modulated wave trains were generated such that the maximum crest appeared at x equal to 12 meters from the wave maker. However, the location of the maximum crest can deviate from x equals 12 meter, especially when the wave breaking occurs. So to obtain the maximum crest height, even in such wave breaking cases, we used stereo imaging techniques to reconstruct a spatial wave profile. For that purpose, 2 cameras were set on the carriage in the tank, like this figure. And in the measurement, we set about 100 spherical floats on the wave surface, and the diameter of these floats is less than 20 millimeter. And these 2 stereo cameras tracked the 3-dimensional trajectory of each float. And from the 3-dimensional coordinate of each float, we can reconstruct the spatial wave profile like this figure. And from this reconstructed wave profiles, we can estimate the maximum crest height, experimentally. So next, moving on to the results. And here we compare the normalized maximum crest height between the HOSM simulation and experiment. And the normalized maximum crest height is plotted against the initial wave steepness AK. And at low AK, low wave steepness, the maximum crest height agrees very well between HOSM and experiment. However, at large AK, the maximum crest height deviates between HOSM and experiment. The maximum crest height in the HOSM simulation continues to increase, while the maximum crest height in the HOSM simulation turns to decrease like this. And this deviation can be attributed to a stronger nonlinearity in the tank experiment. So actually, the wave breaking was observed in this gray shaded AK range. On the other hand, the HOSM simulation cannot reproduce the wave breaking phenomenon. And this is because the free surface elevation zeta is assumed to be expressed as a single valued function with respect to x. And also, this kind of anti-aliasing low-pass filter is used in the HOSM simulation. Therefore, when large wave sufficient to break appears in the HOSM simulation, the energy of high wave number component is filtered out, and the computation can continue beyond the breaking event. Therefore, the stronger nonlinearity in the experiment leads to larger maximum crest height in the experiment than HOSM simulation. But beyond the breaking non-breaking margin, the maximum crest height turns to decrease in the experiment, owing to the occurrence of wave breaking prior to the peak of the modulation. And here we added the Akhmediev breather prediction. And this solid curve expresses the free wave AB solution, and this dashed curve expresses the AB solution with considering the second order bound wave contribution. So this difference means the difference in the bound wave contribution. So therefore yeah, from the difference of these two curves, we can conclude that the bound wave contribution cannot be ignored for the assessment of maximum crest height. And at large AK, we observe a notable difference between the bound wave, second order bound wave corrected AB solution and the HOSM simulation. And this difference can be attributed to the difference in the treatment in the spectral bandwidth. So as I mentioned before, there is no restriction in the spectral bandwidth in the HOSM simulation. On the other hand, the narrow banded spectrum is assumed in NLSE. So therefore, in the following discussions, we will investigate the influence of spectral bandwidth and bound waves to the maximum crest height using the HOSM simulation output. So next, moving on to the discussions. Yeah, here we present an example of the temporal evolution of wave elevations and amplitude spectrum of modulated wave trains with AK equal to 0.105. And only in the vicinity of the maximum crest height time. So from 40 seconds before to 20 seconds after. And from this wave number spectrum figure, we can see that the wave number spectrum varies in time. And the spectrum looks to be broadest at the time of the maximum crest height. So in order to quantify the spectral broadening, we introduce an indicator of spectral broadening, delta K. And delta K is defined as the mean wave number difference with respect to the carrier wave number, weighted by the Fourier amplitude. And yeah, here I present the temporal evolution of delta K. So the delta K gradually increases and reaches its maximum at the time of the maximum crest height, and then turns to decrease afterwards. So the introduction of delta K confirmed that quantitatively confirmed that the spectrum becomes broadest at the time of the maximum crest height. Yeah, and next, to investigate the relation between the initial wave stiffness and the spectral broadening, the relation between the delta K and AK is plotted. And this is the HOSM result, and this is the Akhmediev result. And yeah, and from this figure, we can conclude that the spectrum broadens more as the nonlinearity of the wave system increases. And also we observed a notable difference in the value of delta K between HOSM and AB. And sorry, we skipped the detailed analysis result here, but the cause of this difference is these two processes. The first one is the free wave spectral broadening. So the free wave spectrum broadens more in the HOSM simulation than Akhmediev results. And furthermore, the bound wave production is much larger in the HOSM simulation than the Akhmediev result solution. And this is because in this study, the HOSM simulation considers the nonlinearity up to the fifth order, while the Akhmediev result only considered the bound waves up to the second order. So next, to investigate the relation between the spectral broadening and the maximum crest height, we introduce the amplitude sum AS, this one. this AS is defined as the sum of the Fourier amplitude of all the spectral wave components. And this corresponds to the potential maximum crest height, which is achieved when all the components are in phase at 0. And this is an example of the temporal evolution of normalized AS. And yeah, from this figure, we can see that the AS reaches its maximum at the vicinity of the maximum, in the vicinity of the time of the maximum crest height. And here we present the relation between the spectral broadening, delta K, and the potential maximum crest height, AS. So from this relation, we can conclude that the potential maximum crest height increases as the spectrum broadens. But for a given delta K, the AS, the potential maximum crest height, is larger in the Akhmediev solution than the HOSM simulation. However, the spectral broadening is much larger in the HOSM simulation than the Akhmediev solution. Therefore, a larger AS value is attained in the HOSM simulation than the AB solution. And here to investigate the bound wave contribution, we separate the free and bound wave components from the HOSM output and evaluated the AS for each component. So free wave and bound wave and total wave. So, and in the smallest spectral broadening case, that is corresponding to the smallest initial wave steepness cases, the bound wave contribution to AS is only 9%. However, at the largest spectral broadening cases, that is corresponding to the largest AK cases, the bound wave contribution is increased to 27%. Therefore, we can conclude that the free wave spectral broadening intensified the bound wave production, and this intensified bound wave production is very crucial to the crest enhancement. So, so far we discussed the potential maximum crest height AS. However, the actual maximum crest height is not determined only from AS. It also depends on the phase of all the spectral components. Therefore, next we discuss the degree of phase convergence at the time of the maximum crest height. The amplitude and phase of the waves at the time and location of the maximum crest height can be evaluated from the complex Fourier amplitude of the wave output from HOSM simulation. And these are the example of amplitude and phase spectrum at the time and location of the maximum crest height. And from this phase spectrum, we observed that the phase of almost all the spectral components coincide at 0. So this means that almost a perfect phase convergence is achieved at the time of the maximum crest height. And to quantify the degree of phase convergence, we introduce this parameter D, and that is defined as the ratio between the maximum crest height and the potential maximum crest height. And D is plotted against AK here, and we can see that in all the cases, the D is very close to 1. And this means that the actual maximum crest height is almost very close to the value of the potential maximum value. So almost perfect phase convergence is achieved at the time of the maximum crest. And we also observed a slight decrease of D with AK, and this can be attributed to the difference, the carrier wave is out of phase with other free wave component, and this is related to the phase lock phenomenon, the phase relation among these three waves. So the last is the conclusion. The normalized maximum crest height of unstable Stokes wave trains increases with the initial wave steepness AK in the non-breaking regime, and free wave spectrum broadens owing to the nonlinear quasi-resonant interaction. And free wave spectral broadening intensifies bound wave production, and the phases of all the spectral components nearly coincide at the peak modulation despite spectral broadening. Therefore, these three processes, the spectral broadening and the bound wave production and the phase convergence, are the key and the crucial to the crest enhancement. So that is